Alrighty. It is 6 o'clock. We will be going ahead and starting today or for today's session. And so we are going over Unit 1 multiple choice question set A. If we look at our OneNote here, we can see our review sessions here are going to be in a separate tab in the content library. We have Unit 1 and we have the pages here, multiple choice question set A. And if time allows, we'll look at question set B here. So here's our first question. I will be putting these videos up probably on YouTube. I will be delisting them and only sharing them with our students just so that we can see just within our school here, because this is, I believe, copywritten material by the College Board, and I don't know how they would feel about me just giving away the answers to these, right? Teachers use these as formatives and whatnot throughout the year, and that may undermine their statistical significance. So section 1 of Unit 1 is going to deal with density and the buoyant force. Section 2 will deal a little bit more with the buoyant force and free body diagram specifically and applications of Newton's second law to them. And then the third section will deal with the movement of fluids, which is Bernoulli's principle or Bernoulli's conservation of energy for fluids. So here's our first question. It reads, in an experiment, a student releases an object from rest in 4 different liquids and observes that it observes whether it floats. The results are listed in the table here. Man, the microphone is causing my digitizer to jump. Okay. Which of the following is true about the density of the object? So I'll kind of be doing these as mini polls here for y'all. I'll run them for maybe like 10, 15 seconds. There's only 2 of y'all. So if I do see that, you 2 have submitted an answer, I'll go ahead and roll with it. And so we have different material or fluids that it has been submerged in. They give us the density of the fluid, and then they tell us whether it sinks or floats. And the question is, which of the following is true about the density of the object? Howdy, welcome. If you want, you can go ahead and follow in the AP classroom here. It will be Unit 1 progress check. You click on Unit 1 at the top and then scroll all the way to the bottom. And then let me bring up the chat just in case there are any questions in the chat. And so we have our first poll here. I'll be running these for about 30 seconds a piece. This one, we're getting our bearings here going, so it could take a little bit more time. All right. And so I'm going to go ahead and hide the meeting controls here just to make it a little easier. Okay. So if we look at this scenario here, oops, I'm pushing too many buttons. Okay. All right. So if we look at this, we've learned that an object floats when its density is less than the surrounding fluid, and it's going to sink if it is more dense. So if we notice, right around 850, it sinks, but after we've put it in salt water, which happens to be 1,025 kilograms per meter cube, it floats. As a matter of fact, we have an even better estimate here. So it looks to me like the density of this object is going to be somewhere between those two. You have to leave at 6:30. Okay, no worries. Have fun at your piano class. I will be putting these videos on YouTube. I'll send you guys a link, and these will be delisted just so that only my students have access to them. All right. So if we look at this, it looks to me like C is our best answer. It is the density is between that of distilled water and the density of seawater. So well, bam. Okay, let's go ahead and look at number 2 now. We'll relaunch the polling here. And so the question here is, a student wants to determine whether the density of a solid cube of copper will decrease as its temperature is increased without melting the cube. Graphing which of the following will allow the student to study this question? It's causing my digitizer to act up. Okay. And so we have about 3 submissions. We'll go ahead and submit it here. And so just by looking at y'all submissions, it looks to me like most of us are thinking maybe B is our best answer choice. So if we don't melt the cube, here's a big hint here. If the cube does not melt, the mass is going to be constant. just because it stays intact. We're not going to lose any. It's not going to drip out or separate. And so the mass is constant. And so we're trying to see some kind of density relation versus temperature. So one of them is going to definitely be a measure of temperature. Now, because the mass is constant, that one's going to be not helpful, and neither will this one. Okay. The other thing is, well, we have temperature as a function of time or volume as a function of temperature. So if we remember the density of an object is the mass over its volume. And so here, if the mass is constant, we could say that the density is inversely proportional to the volume of the object. So by looking at the volume of the object and it's as the temperature changes, maybe we could do something like this, we can get some idea about the relationship with the density, because I think we would expect the volume to increase as we heat this up, the molecules expand, and so we would expect the density as a function of temperature to maybe be inversely related like this, because the volume is increasing. So we get less density. So water is the one thing that kind of, or not the one thing, but is one of the few things that happens to kind of go against this. Water is the one thing that, well, also they said no melting, so we'll kind of call it there. All righty, let's go ahead and look at number 3. Students are investigating the change in density of water as the temperature of water increases. Students measure the mass and the volume of a quantity of water and then heat the water to various temperatures in the range using a thermometer to measure the temperature. I think there's a little bit more to this. They then attempt to determine the density of water at different temperatures. Assume any changes of equipment or measuring tools due to temperature changes are negligible. Which of the following methods would allow students to obtain data from which they could determine the change in the density of water at different temperatures? So let's see here what we're thinking. Relaunch polling. The thing about trying to upload this to It's Learning or Teams is that there is a file size limit, at least for It's Learning. I'll try uploading to Teams and put them in the file section of our respective class periods. But if not, I will share the link on YouTube for you. Okay, and we have about 2 answers here. I'll go ahead and call it here, just to kind of. And so this is very similar to the previous question. The amount of water that we're going to be talking about, the mass is not going to change. And so we're looking for a change in density with different temperatures. We're going to want to record the temperature of the water and take precise measurements of that volume of water. So we can put this in a graduated cylinder and then heat it up and see how the water expands. Record the mass of the water and precise measurements of the volume. While this would give us the density, we have no way of tracking the behavior of that density with temperature. So that's why that one's not very good. And then submerge a cylinder, this would probably just kind of give us the density of that cylinder. This is the Archimedes method for density of an object. And then record the temperature of the water with precise measurements of the mass. Again, we want to see that volume change because the mass is going to remain constant. So here, the only reason why this one doesn't work is mass is constant. And we want to see how the temperature changes the density, and the mass is not going to change, the volume will change. All righty, question number 4. And let me know if I'm moving too fast or if I'm moving too slow. So in an experiment, a student puts 3 different objects, each of 3 objects, A, B, and C, in 4 different liquids and observes whether the objects float. The results are listed in the table. Which column contains information that is most useful for estimating the density of object C? Okay, we'll go ahead and call it here in about 4 seconds. Sorry if you don't really get to ruminate. And if you don't feel like you have an answer, it's okay. You could take a guess or not submit an answer. Don't feel pressured. Just kind of trying to get a little bit with the pacing. All righty. So if we look at C, it's going to sink in gasoline versus floating in distilled water, and it also floats in oil. Now, if we look at the density here, it looks to me like the density of this object is probably above 737 because it sinks, but it's probably right below or right around 850. So it looks to me like because these densities are the closest to each other, this will give us the most meaningful estimate of the density of the object. And so in this case, that is going to be gasoline and oil. And again, let me know if you guys have questions over these. And we'll, we can definitely take some time to address your thoughts and concerns here. Okay, question 5. A physics teacher gives a solid object to each student in her class. The objects are each made of the same material but have different shapes and sizes. The teacher asks the students to measure the mass and the volume of their object and work together to determine the density of the material from which the objects are made. Which of the following methods will give the best estimate for the material's density? So here we have another experimental situation. And let's see here what we're thinking. All righty. So in this case, some of these sound pretty good, but one of the most stressed approaches for doing any kind of experiment, especially with a college board, is you want to make graphs, you want to make plots, and you want to work with lines of best fit. And so in this case, A sounds really good. We can divide the mass of the object by its volume, and then we get the density of the object, and then we get the average of all the densities. This sounds really good, and it's an okay approach. Definitely, this is the way we do it in IPC and to an extent introductory physics. But the College Board really stresses graphical analysis for experiments. So it's best for us to create a graph plotting the mass as a function of volume. And here, the slope of the best fit line is going to give us the density. And that's just because density is the mass over the volume. Okay. Because there can be a lot of variability, we could have a very massive object. And granted, its volume will also be very big. Here, very massive objects or very voluminous objects are going to have a shift on the average mass and the average volume of the objects that you are working with. So this could also give you a density, and it'll be close, it should be, but really the best method here is going to be C. And again, let me know if you have questions over that. But I kind of feel like this is a got you, and part of it is trying to remember here the graphical approach that the College Board stresses. Question 6. Water is poured into a U-shaped tube and allowed to come to rest, as shown in the figure. Which of the following can help explain why the water in the left and the right sides of the tube reaches the same height? We're going to select 2 answers. So let me go ahead and change the poll here, just so that we can see which 2 answers are the most popular. Okay. All righty, 15 seconds. This one was quick. All righty. So let's see here. So we have learned that when fluids are open to the atmosphere, or to air, sorry, atmospheric pressure pushes down on them. And so if the atmosphere, for whatever reason, was greater on one side, then that would push the fluid further down by exerting that force over an area. So I'm going to agree that the force exerted by the atmosphere on the surface of the water is the same on both sides. You could, put your mouth here and then blow on it, And then that would also exert a pressure, and that would cause the fluid to come out of the other side of the tube. So definitely the pressures are going to be the same on both sides. And in this case, it's open to the air, so it's atmospheric pressure. The other part we've learned is that weight. If I look at this region down here, we have the force due to all that hydrostatic pressure, the pressure due to this water standing on top of it. And so if one side has a heavier fluid than the other, that heavier fluid is going to push, and it's going to decrease its height if it's denser, so that the other guy has more height to pick up for more pressure, to equalize that pressure. And so I would agree, yes, D, the weight of the water on the left and the right halves of the tube are the same. Very nice. Okay, let's go to question number 7. A wooden cube is floating at rest on the surface of a liquid. Which of the following is an action-reaction pair of forces? Man, these are always gotchas, I feel. That can explain why the force exerted by the liquid on the bottom of the container is greater with the floating cube than without it. Oops, not that pole. I should just delete all these other old poles and just leave these two. Alrighty. Would the graph slope be more accurate than just finding the average, or is it just the College Board? So because you would need to probably take a lot of little, like, you would need a lot of densities so that the average density is close enough to the best fit line. The best fit line kind of helps minimize those errors, because if we graph this, we're going to have kind of density dots. Sorry, I just saw your question there. And so in this case, if we get these averages, we'll get close to the density. But there's something called what is it called? The deviation of the values. And so what ends up happening is the linear regression, or getting the line of best fit, is going to minimize these deviations. And so this is why the line of best fit is generally considered better. Whether it's College Board or not, this is just kind of considered best practice. It's a little more tedious to draw a graph and get the line of best fit and do linear regression analysis, but it'll work better than getting the averages. Because if you have very large deviations from the mean, that is going to shift the mean much more due to its influence. But the line of best fit generally minimizes the deviations, which is going to alleviate that issue. Hopefully that answered your question there. So takes the statistics, and then when you guys get to linear regression, you'll see what's up with that. Alrighty, so we need to find an action-reaction pair that explains why the force exerted by the liquid on the bottom of the container is greater than with a cube in it than without it. So the earth exerts a gravitational force on the cube, and the liquid exerts a net upward force on the cube. Hopefully we recognize that this is the gank. Definitely the water reacts to the cube being placed on it and it pushes up, but that is not an action-reaction pair. The College Board, remember, we want the two things, and nobody chose this answer, but so we can go ahead and skip it because it seems like we got that idea. Let's see here. B, the liquid exerts a net upward force on the cube, and the cube exerts a contact force on the liquid. So here's our action-reaction pair. If I have a force from the liquid on the cube exerts a force on the liquid. We just literally, to find the action-reaction pair, we generally want to swap the words, by and on. And so B is going to be our best answer choice. Let's go ahead and look at the other ones. Earth exerts a gravitational force on the cube, and the cube exerts a gravitational force on the earth. This is true. This is very much an action-reaction pair. The problem with this is it does not explain why the force at the bottom is greater. Boot at the bottom. At the bottom is greater. Okay. So in physics 1, this would have probably been our best answer choice for an action-reaction pair. But again, it doesn't explain why. Because if I have my container of water, by me putting an object in there, the object exerts its weight on the fluid, and the fluid is going to fight back by being pushed out. And so because we're pushing down on the water, that force is transmitted to the bottom of the container. Let's see here, D. The earth exerts a gravitational force on the liquid and the liquid exerts a net upward force on the cube. So here, this is not an action-reaction pair. It sounds good because it kind of answers the question here. And these are true ideas. The liquid definitely exerts an upward force on the cube and the earth definitely exerts a gravitational force on the liquid. And like implicitly, it does explain why the force would be greater, but it's not an action reaction pair. So that's why B is our best. Just realized you misread my answer choice, pain. It happens. That's why we practice these so that we're aware of like our potential mistakes to minimize those in the future. Question number 8. A block of weight W is floating in water and 1/3 of the block is above the surface of the water. Which of the following correctly describes the magnitude F of the force that the block exerts on the water and explains why F has that value? So let's see here. All righty. So we are at an impasse, 50-50 between B and C, because we've learned that if an object floats with some height above water, we can get a ratio of the densities. But here they are asking specifically for the force that the block exerts on the water. And so we know that the block has a weight W. If we go back to our previous example here, the block is going to push with a force W on the surrounding fluid. Now, if it remains at rest, if it floats, the net force has to be equal to 0. So we have the force from the water minus the weight equals 0. So this tells us that F, the force that the block exerts on the water, has to be equal to the weight. And it's only because it's floating. D sounds pretty good. No one went with it. But it's a gotcha. Any object will always exert a force on the surface beneath it that is equal to the weight. Not true if it's accelerating. We can kind of think of it as our elevator situation. If I'm accelerating downward, that means that the downward force is greater than the buoyant force. If I'm accelerating upwards, the buoyant force is going to be greater than the weight. Alrighty. And then B. So what we would find out is that the ratio of the density of the block to the water is probably something like, how do we get it? The H submerged over the height of the object is the ratio of the object over the ratio, the density of the fluid. The water. So here, the important thing here to recognize is even though it floats above or below by a certain amount, that force is still has to equal the weight. All right, let's go to question number 9. A cube submerged in a rectangular tank of liquid is at rest. Which of the following is a Newton's third law pair of forces in this situation? Okay. All righty. So before the buzzer. So let's see here. Most of us were thinking B, the force that the liquid exerts on the side of the tank, and the force the side of the tank exerts on the liquid. So yes, very good. The quick way to do this is to just switch the wording here. And if the switching the wording creates the other statement, then it's true. Let's see here. The force that the liquid exerts on the side of the tank and the force the liquid exerts on the side of the cube. So here, because this is still true, the force will be equal in magnitudes as long as everything is at rest. But again, we got to find the Newton's third law pair. And if I'm talking about a force on an object due to me, then that object is going to be exerting a force onto me. And so B is our best answer choice. Definitely, as the side of the cube pushes on the fluid, that force will be transmitted to the side walls of the container. But here we need to find the two objects interacting with each other in the statements. Oops. All right. The figure shows a block of wood floating in a beaker of water. Which of the following is true of the force exerted by the wood on the water? All righty. So most of us are thinking B. Let's see here. The wood exerts a downward force on the water that is equal in magnitude to the weight of the wood. Yes, that is true. The wood exerts an upward force on the water. And that is not true. Because I am placing the block onto the water, it's going to push down with its weight. Its weight is directed downward, and so it's going to push down on the water, not up. The wood does not exert a force on the water. That's magic right there. That is not true. The wood exerts a downward force on the water that is equal in magnitude to the upward force exerted by the beaker on the water. Not true, because the bottom of the beaker has to contend with the downward weight of the block plus the weight of the water above it. So the bottom, this explains why the pressure is greater, because we have all that water exerting its weight on us. Let's go ahead and continue on the next one. Question 11. A block of mass M is floating in a container of liquid and is partially submerged. The block is then replaced by a block of mass 2m. Which of the following describes two forces that are Newton's third law force pair, whose magnitudes are the same for the two situations? I'm going to say this one's a little tough. Okay. And we'll see here, maybe one more. Yeah, this one's a stumper. Okay, we'll go ahead and call it here. So one person said B, one person said D. And so when I first did this question, I was thinking B, because B is a very good statement of Newton's third law. Can we assume that the volume and the density is constant? For which one? Number 10 there? Sorry, Juan, I just saw your question. For number 11. Oh, okay. So we don't know. We cannot assume that. If they told us if it floated or if it sank, that might tell us something. And we could infer there from there the density or the mass. But all we know is that the first block floats, but we don't know anything about the second. So in this case, I'm calling it at 30 seconds just to allow time for me to explain it and not go over time. You officially should be spending about 1.8 minutes per question. So that's going to be what, like about like a minute 50 seconds. I'm calling it at 30 just to kind of like rush you and kind of train you guys for a faster kind of approach if need be. So here, while I do agree that the gravitational force the Earth exerts on the liquid is an action-reaction pair to the gravitational force the liquid exerts on the Earth, that is true. This does not explain the question as to why the pairs would be the same as before. Okay, then if you want, I can go ahead and slow it down a little bit more and give you more time to think about it. Sorry about that. Okay, all righty. So what we know here is that in two scenarios, these pairs will be equal to each other. And so this has to be addressing, or the answer has to be addressing the fact that we have placed a block in there. And so it turns out our best answer choice is C. The force the liquid exerts on the bottom of the container, because here, this takes into account the new block that has been placed, as well as the old one. And regardless of either scenario, the force that the liquid exerts on the bottom of the container will be the same magnitude as the force that the bottom of the container exerts on the liquid. These two forces are equal and opposite, and they're the action-reaction pair. Now, from scenario 1 to scenario 2, they will have different values. But the pairs themselves will still be equal in the two situations when we change the block. Here, this does not address the fact that the block has been placed, and while it is true and an action-reaction pair, it doesn't really hit it on the head for the scenario. All right, you got to go this? Okay, so yes, I'll post the link on this in Teams. I'll send you guys. I'm gonna try to upload it tonight, along with the physics one. Okay. The force the liquid exerts on a block and the force the block exerts on the liquid. So this one, actually, you know what? Let me check. Let me make sure it's not D. I wouldn't be surprised because D also sounds good. Let me see here. Sorry about that. Let me just take some time here. And we can go here. And this is question 11. 11. And the answer is, oh, shoot, I was wrong. Yeah, B is correct. I'm sorry. I am sorry. So they say the mass of the liquid does not change, so the gravitational force remains the same. Sorry. And the values of these forces would be different. So for C, even though I was advocating for C, I do apologize for that. D is not even. Well, I'm glad I still thought D sounded good to go check the answers. So they are actually saying here, I misread the question. The magnitudes will be the same in the two situations. So because the water is still the same amount of water, the actual force of the water, the weight from the water will be the same. It would, and that's why C is not true, because the force in the two scenarios are different. And I did say that, but they want us to answer in which scenario will the force, or sorry, in which of these answer choices is the force the same in both scenarios? And the weight of the water is the same in both scenarios because it's still the same amount of water. These forces are an action-reaction pair and they will be equal to each other, but they will not be the same in both scenarios. And that's here what they want us to address. Find the force that does not change when you put the block in there. And when you put the block in there, you're going to be exerting more force on the bottom because the block is pushing down on the water. And let me know if we have questions over that or if that makes sense. And then this one's not true because in scenario 2, if the heavier block is pushing on the water, that amount of force will be bigger than before. Okay, there's only 13 questions in this one, but we still have plenty of time. I think we're going to do section B as well. A sphere made of gold is moving downward through liquid mercury at an increasing speed. The mercury exerts a net buoyant force in the upward direction on the gold sphere. Which of the following describes a Newton's third law pair for this force? Man, Newton's third law really stressed in this section here. So for those of you guys that got B, yay, good job. So in this scenario, let's see here. The gold sphere exerts a force on the mercury with a magnitude equal to the weight of the gold sphere. That sounds pretty good. The thing is, it is moving down with increasing speed. It is accelerating. So what ends up happening here is the buoyant force does not equal the weight. And when I push down on the water, it creates this buoyant force. So as I'm pushing down on this water, the mercury or the mercury sphere, sorry, the gold sphere, pushing on the mercury is, in this case, it is going to be pushing with more than the weight. So it's not going to be actually equal to the weight. What ends up happening is, again, as I push on the water pushes back with what we call the buoyant force. And so what ends up happening is B is our best answer choice. The gold sphere exerts a force on the mercury with a force equal to the buoyant force. Let's go ahead and look at C and why it's not the best answer choice. Earth exerts a gravitational force on the sphere with a magnitude equal to the weight of the gold sphere. That is true, but it is not explaining this net buoyant force going on here. If we look at the explanations on the College Board, for C, they say the weight of the sphere is the gravitational force exerted on it. So this statement is saying something is equal to itself. And while it is true, it is not a third law action reaction pair. For B, for answer choice A, it is true that the third law counterpart to the buoyant force exerted on the mercury will be the force on the mercury. However, forces that are third law pairs have equal magnitudes. Since the gold sphere is accelerating downward, the magnitude of the buoyant force exerted by the mercury is less than the weight of the gold sphere. So not equal in magnitude. They are action reaction pairs, but they are not equal, which is the other part to the action reaction. Okay. We have a submarine with a mass of 3.6 times 10 to the 6 kilograms, and it is submerged in water and at equilibrium. Inside the submarine are ballast tanks filled with water. Some of the water in the ballast tanks is then ejected. So it was in equilibrium before, but we are ejecting water, decreasing the density of the submarine. We now have empty air or air taking up that space when it used to be water. The free body diagram of the figure shows the magnitude and the directions of the forces acting on the submarine after the water has been ejected. And the acceleration of the submarine is most nearly. So let's see here what we are thinking. Yeah, who thought we'd have to bust out a calculator today? As we've noticed, right, even AP Physics is like hardly any calculation these days. It's like proportions and procedures and applications of principles. Okay, we have our answers. Let's go ahead and calculate this. So if we do Newton's second law, we can go ahead, and they just want the magnitude of the acceleration. I'm going to go ahead and just choose the bigger number as the first force. So that's what, 4, whoa, 4.0. Oh no, my tablet is wigging out. Times 10 to the 7 newtons. Sorry, it's going to be the buoyant force. I may need a charging. Come on, man. It is the buoyant force minus the gravitational force equals m times a. And so 4.7 minus 3.6 times 10 to the 7 is going to be 0.6 times, oh man, this is really bad. Let me turn it off and turn it back on. In the meantime, the correct answer is D. So 0.6 times 10 to the 7 is the same thing as saying 6 times 10 to the 6 divided by 3.6 times 10 to the 6. That is terrible. I'm going to try to find the cable for this bad boy, and then we'll go ahead and look at the last question here for now. A sphere of mass 0.5 kilograms is dropped into a column of oil. At the instant the sphere becomes completely submerged in the oil, the sphere is moving downward at 8 meters per second. The buoyant force on the sphere is 4 newtons, and the frictional force from the fluid is 4 newtons. So there's viscosity here. That's not something we really talk about, but we just treat it as a frictional force and we know its number. Which of the following best describes the motion of the sphere at this instant? Oh, yeah. 4. Sorry. Yeah, I did bad math. Right, 40 minus 36 has it leaves you with 4, not 6. Thank you. Really appreciate that. Yeah, so this is just F equals ma. Net force equals mass times acceleration. Yeah, but you still got D. Okay, nice. Give me 1 second. I'm gonna try to get a cable for this guy. Shit. Okay. So in this case, if we look at this half-kilogram sphere, it weighs 5 newtons. Its weight, is mg, 5 newtons, because 0.5 times 10. But if we notice, as this object is sliding downwards, we always have that, well, not always, but we do have that buoyant force acting upwards. And we have the frictional force. Well, if this thing is moving downwards in a fluid, then the frictional force is going to prevent that sliding motion, and the friction will act upwards. All right, let me see here. Okay, hopefully here. No, what the heck? Okay, there we go. I can feel it being more seamless. Okay, so we have the force from the buoyant force, we have the force of friction acting upwards, and then we have the weight. And so that's going to be 8 newtons up, 5 newtons down, with a velocity of some number downward. So we have a net upward force. If I'm moving downward, but my force is upward, then my acceleration is in the opposite direction, and I will be slowing down. So the sphere is moving downward, not at a constant speed, but with a decreasing speed. You see here. The sphere speed is increasing while the sphere continues to move downwards. Not quite. The sphere's speed is increasing while as the sphere begins to move upwards. Not quite. Does that make sense? Maybe here, like it was dropped, and then eventually it's going to come to a stop as the velocity becomes 0, and maybe it'll float. But as we get deeper, the buoyant force gets bigger and bigger. So it's going to come to a stop and then probably rise to an equilibrium point. Does that make sense for number 14? Does that answer y'all's question there? A couple of us chose other answers. Okay. All right. Let's go ahead and look at questions for multiple choice B. So I'll give you guys some time to transition into that one. And let's look at free body diagrams. Oh man, I'm debating what to have for dinner. Hopefully I'm not impeding on y'all's dinner time. So I'm gonna try to make these as like homework assignments, just to like have an easy grade for y'all. So I would do them on AP Classroom if you want, just to kind of get the answers, and you could submit them now or you could save them for later. It'll give you the answers and give you explanations for them that are more concise than mine. And then, okay, you have to go by 7:30. Okay, all right, so there's some time. But yeah, I don't know, kind of craving something spicy. Anyways, let me know if you guys are ready for question set B on unit 1. Okay. The other thing, you know what? Let me pause the share here for now. Let me open up a calendar just so that you guys can jot down what. Let's see here, calendar.google. Just so that you guys can see what days I have planned out for our sessions. we do have that UIL meet on Saturday, which will kind of impede into the time here a bit. So let me go ahead and do a new share. And so you guys can see my calendar here for Physics 1 and Physics 2. So today we're doing Physics 2 Unit 1. Tomorrow it's going to be Physics 1. And so if you have any friends, because I know one of y'all's peers or some of y'all's peers are taking Physics 1 again. I think Sebastian is one of them. Oh, I probably shouldn't say names because they're being listed. And I should try to like address y'all anonymously. But I mean, I'll put this on YouTube and only like the classes will see them. But if you have people that are challenging the Physics 1 exam and they want to come into my review sessions, they're more than welcome to. And so for tomorrow, I'm going to be going over Unit 2 multiple choice B questions, and that'll be at 6 o'clock. On Saturday, we will be meeting at 5 p.m. if you guys can make it on Saturday. And we were going to be practicing the free response. And this is scheduled from 5 to about 7. Next week, Mondays, Monday it's Physics 1, Unit 3. Tuesday will be Physics 2, Unit 2, multiple choice. And then again, we will meet on Thursday for Physics 2, Unit 2, multiple choice B. I'm thinking if we can run through a good chunk of them in one sitting, I might consolidate them just so that I can cover more topics here. Because according to my calendar, for Physics 2, we're going to get to about Unit 5 out of 7. And y'all's exam is technically on the 7th, Friday. You are allowed multiple testing dates, but I think by now the AP coordinator has decided what days you guys will be taking your exams. So I think most of us are going to be taking it on the 7th, which will leave us with a little bit of topics not reviewed in the evening sessions. But hopefully that still it still adds to enough into your preparation. In addition, the College Board will be having their live sessions for Physics 2. And I can get you guys that link here in a bit, but we'll go ahead and get started with these questions here just so that we can work through it. So a solid cube is submerged in a container, so it's completely covered, and the cube has a mass of capital M, a volume VC. Oops, I just saw the chat. Somebody maybe had to go. Okay, alrighty. No worries. We'll see you tomorrow. Have a good one. I'm so sorry. I didn't see this message until right now. I had hidden the chat, but take it easy. Have a good one. And then again, you should be able to find the solutions to these and the explanations. Okay. So the cube has a mass m, a volume VC, and a density of the density of water over 2. And the water exerts an upward buoyant force on the cube with a magnitude equal to rho Vg. Which of the diagrams best represents the forces exerted by the water on the cube? Let's go ahead and do a poll. Let's see here. Which of these do we think is the best free body diagram? And so a lot of this setup here for the first question is probably not that needed for this question, but for the following one it will. Okay, so let's go ahead and take a look at this one. So if we notice, it has half the density of the water. So this thing should float, but it is submerged. So we have put it in a situation where normally it would float, and we've put it in a state of sinking. Because normally, if this has half the density of the water, it should float such that half of it is underwater. But as we push it deeper and completely submerge it, we now have more water displaced or more water pushed out. So the buoyant force here is going to be larger than the weight. The buoyant force that they told us here is rho Vg. Oops, rho Vv. Whereas the weight of this object is going to be the mass, which is rho v. This is the mass of the cube, times G, and the density of the cube is going to be the density of the water over 2 times V times G. So what we find out is the weight is going to be half the buoyant force. So these arrows are going to give us those magnitudes. So we need to find a scenario where the downward force, oh, not only that, in this case, sorry, they're just asking for the forces on the water. As we go deeper, the bottom feels more force. So automatically that's C. Even my explanation here would give you the explanation for that C is the answer. We could say, well, this is the weight and this is the buoyant force. But more than anything, the water on the top, there's less water pushing on the bottom. And over here, we have more water pushing from the bottom. So we're going to expect more force on the bottom of the cube than on the top. That's what gives us that buoyancy effect as we push water out. Now, this is kind of lame because the difference between this force here and this force here for a small cube, sorry, I messed up there. Why would it be half? So if I have half the density of water, then the weight of that is going to be the density of the cube times the volume of the cube times G. And they told us that the density of the cube is the density of the water over 2, but that's not necessary for this question. Now, in reality, they just want us to see the forces exerted by the water on the cube. So if this cube is small enough, the difference between the top and the bottom forces is really small. But it's still enough to create a buoyant force. Because remember that as we go deeper, the pressure increases. And so that pressure exerted on that area will increase on the bottom versus the top. So we should have less of water force on the top than the bottom. And the difference between those is what gives us the buoyant force or the net buoyant force. Let me know if that answered the question. Here's this bad boy number 2, which is actually what I was thinking of answering earlier. Okay. A solid cube, it's the same scenario as before, is submerged in a container of water with density rho W. The cube has a mass V, a volume B, C, C being for the cube, and a density equal to half the density of the water. The water exerts an upward buoyant force equal to the density of the water times the volume of the cube. And that's because it's submerged. So the water displaced, the volume of the water displaced is the volume of the cube. What the heck? I opened up another OneNote. Volume of the cube. Okay. Times G. And the question is, if the cube is released and allowed to rise, what is the magnitude of the acceleration of the cube immediately after release? Let's see here what we're thinking. Okay, and I'm going to go ahead and start going over it, but if you're working it out, that's fine. So we're told that it's rho W V times G, and this guy here is going to be rho over 2 VG. So one way we can see this is we have the buoyant force minus half the magnitude of the buoyant force. So we really should write it as the weight, but we're saying that this is half that quantity. And that's just because it's half the density. Equals m times G. So here we can write it as rho Vg minus rho Vg. This is probably the more proper way, over 2 equals rho over 2 Vg. Oh, sorry, we're looking for the, and sorry, not mg, ma. This is Newton's second law. So if we look at this, this kind of cleans up. This becomes rho vg over 2, because a whole minus a half is a half, equals rho over 2 vg. And so the volumes cancel. And then we multiply this by 2, divide by the density. The densities also cancel. And I feel like I made a mistake because the answer is half of g, but my math is not showing that. Where did I go wrong? I lost a half somewhere. Somebody help me. Because one of you guys actually got it. And this is A, not G. My goodness. I am so sloppy. I'm starting to get tired. I'm sorry. I'm making a lot of silly mistakes. Oh, wait, no, it's not half a G then. I'm going to say it's G then. Let me check the College Board real quick because, ooh, bail me out, glorious College Board. This is embarrassing. So it goes. It's like question number 2 and I'm already fumbling. Oh, no, yeah, the answer is G. I guess I just wanted it to be a half. No saying nice things about the college. Well, we'll hold off there. I'm only saying nice things because this is being recorded, right? Just kidding. Okay, so it is BG. The acceleration is equal to G. All righty. So A equals G. My 2's canceled out. I don't know why I was thinking it was half. Okay. So let's go ahead and look at the next question here. So it's the same scenario as before. And it says a solid sphere of unknown mass and twice the volume of the cube is then submerged and released. The sphere is observed to have the same acceleration immediately after release as the original cube. And the question is, which of the following claims can be made about the density of the sphere? Alrighty. So if it has the same acceleration as before, what we saw was that this was essentially the acceleration was given by the density of the water times G minus the density of the material cube times G. Oh, no, it's okay. No worries, no worries. No rush. So basically, if we're gonna get the same acceleration as before, and it's still the same liquid, really, we're just looking at the density of the cube. And if we have the same acceleration as before, we're gonna have the same density. And it just so happens that if it has twice the volume and it has the same acceleration, it tells us that the density is the same as before, but for twice the volume, we have twice the mass. And so that effect kind of fixes itself. So C is our best answer choice here. Question number 4. In the lab, a student is given a glass beaker filled with water with an ice cube of mass m and volume Vc floating in it. So the cube has a mass m and a volume Vq. The ice cube displaces a volume of Vd of water as it floats. The density of the water is rho W and the density of the ice is rho I. The water exerts an upward buoyant force with a magnitude equal to rho of the water, the density of the fluid, times the volume displaced, times the acceleration due to gravity g on the ice cube. Which of the following is equal to the magnitude of the force that the ice cube exerts on the water? So let's see here what we're thinking. All righty. So if it floats, the buoyant force equals the force that the cube exerts on the water. Now it will be its weight if it's floating here, and then, but if we notice, they want us, they want us to find this out. Well, the buoyant force is given by the density of the water times the volume displaced times G. So it turns out A is an underhanded answer choice, but it is correct because it's really just the buoyant force. And so this is the quickest way to calculate it. Because if we look at B, and neither of you chose it, the density of the ice would need to be the volume of the cube here for it to be correct, because this would give us the weight, the gravitational force of the cube, and that's the force that it's going to push the water with. If we look at this, the cube is not made out of water. So if we calculate this, this would be the buoyant force if we manage to submerge the cube. Okay, so not quite. It's floating, so it's just going to be the buoyant force. And so our best answer choice here is A. Let me know if that answered your question there. Or if you have questions about that, let me know. In the lab, a student is given a glass-filled beaker with ice, and it's the same situation before, and they say the downward force of gravity on the ice cube has a magnitude equal to Fg. The student pushes down on the ice cube with a force of magnitude Fp. Oops, sorry, I just saw that light up. You got it right on accident. I was just banking on action reaction pairs, but that's kind of it. I mean, remember that if the force, the cube pushes down on the water pushes up. The buoyant force is that force that the cube is pushing down with. And so it is correct line of thinking. They're action reaction pairs. And you just kind of had to find, okay, well, which of these is the correct explanation? So no, you're good. And so the student pushes down on the ice cube with a force of magnitude Fp so that the cube is totally submerged. The water then exerts an upward force on the cube of magnitude Fb. And the question is, which of the following is the expression for the magnitude of the acceleration of the ice cube when it is released? So we were pushing down on it to submerge it, and then we release it. And they want us to find out which of these equations will give us the net force on the cube, or sorry, the acceleration on the cube. Plot twist, you need the net force. Okay. All righty, so let's go ahead and see here. Oops. I drew this the wrong way. So at the beginning, we're pushing down with a force Fp. There's the gravitational force acting down on it. And then we have that buoyant force acting up. When we release it, geez Louise, that's me. No, stop opening OneNote. Okay, whatever. When released, the push force, or the force that we push down with, goes to 0. So then the net force will be the buoyant force minus the force due to gravity equals m times a. And so the acceleration is just these two. Because it has been released, the pushing force is no longer there. And that's why B is our best answer choice. Hopefully that made sense there. Almost there. Question 6. A 1 meter by 2 meter by 3 meter rectangular block has a uniform density of 600 kilograms per meter cubed and is completely submerged and held stationary in a deep pool of water. the water exerts an upward buoyant force on the block of 6 times 10 to the 4 newtons. 60,000 newtons is the buoyant force. When the block is released after rising a short distance towards the surface, it experiences a drag force of 20,000 newtons. The magnitude of the acceleration of the block at this instant that the drag force is that much is most nearly. So let's see here what we're thinking. Not properly drawn. 1, 2, 3. Okay, so we can go ahead and calculate the volume. I believe it's 3 times 2 is 6 times 1 is 6 meters cubed. We have a density of 600 kilograms per meter cubed. And so that gives us a mass of 3,600 kilograms. When we multiply by G, which is roughly 10, we get a gravitational force or weight of 36,000 newtons. Now, in this instance, our cube definitely feels a gravitational force downward, and we have a buoyant force upward, which in this case happens to be 60,000 newtons. It's 4 zeros. Now, when the block is released and after rising a short distance toward the surface, it experiences a drag force. So this bad boy is rising. So the drag force is going to be downward with the magnitude here that they gave us. Let me see here what it is. 20,000 newtons. Okay. So our net force is going to be the 60,000 from the buoyant force minus the 20,000 newtons from the drag. And that gives us 40,000 newtons. But then we also have to subtract the weight, which is 36,000 newtons, which I think is kind of like the submarine question from before. At least the numbers look similar. And so this gives us 4,000 newtons. And that's going to be equal to m times a. And the acceleration here is going to be 4,000. Let me know if I made a mistake in the math. Divided by 3,600 kilograms. Oops, not that one. Wait. Did I cancel out this? 4,000 over 3,600. Oh, I probably shouldn't erase that. It's 40 over 36. And that's going to be 10 over 9. If we factor out a 4, right? And so that becomes about 1.1 meters per second squared. Did I do that right? I'm just kind of like mental mathing it. Looks about right. Good enough for government work, right? If all else fails, like the other answers are kind of far off. So just by order of magnitude analysis, we could see here, okay, we have about a 4,000 force, Newton force, and this thing has 3,600 kilograms. So it's going to be on the order of 1-ish when we divide them. Alrighty, number 7. A sphere of density rho s, S for the sphere, and volume V is submerged in a fluid with a density rho fluid, rho P, or sorry, rho F, which exerts a buoyant force of magnitude, the density of the fluid times the volume displaced times G. Immediately after being released, the sphere moves upward with an acceleration of magnitude A. Which of the following changes would result in an acceleration with a greater magnitude immediately after release? Okay. So we want greater acceleration. What we have seen here is basically it's rho of the fluid minus rho of the object equals rho times the acceleration. Oh, and then there's a g here. Sorry. The b's kind of cancel out. And so it's going to be the difference in the densities times the acceleration due to gravity, and this would be the density of the object, divided by the density of the object. So we can either decrease the density of the object, because this will give us a larger acceleration. We get a larger numerator and a smaller denominator, but that's not an answer choice here. Increasing the volume but keeping its density constant, that's not going to change anything because the volume displaced here for this guy is going to be the volume of the object either way because it's submerged. So those cancel out here. And that would also be the volume here of the object. So if it is submerged, the volume displaced is the volume of the object. So changing the volume doesn't do anything. And if we keep the density constant, well, that's also not changing anything. So C is not going to work out. Maybe we're thinking increasing the air pressure on the surface of the liquid. But if it's in a container here and it's submerged, whatever pressure we exert here is going to get transmitted into the fluid. And so really what we need to do is we need to increase the density of the fluid here. Okay. So just like if I push harder here, that force will be transmitted to the bottom. But if I push harder, that force will be transmitted directly to the top here, and it'll balance out. It won't change anything here. Let me know if that makes sense here. We could try releasing it deeper in hopes that the pressure is greater, but the difference in the pressures is still going to be the same because the difference in the pressure between the top and the bottom, delta P, that's the hydrostatic pressure, is rho G like delta H. And the difference in the heights here would be the same even if we put it in a deeper situation. Unless our fluid happens to be compressed due to its own weight, increasing its density. Let me know if we have questions over that one, just in case. Question 8. I'll move on, but I'll address them here in the chat. A small submarine is underwater and moving horizontally at the same constant speed as the northward current in a straight level section of a river. It releases a sensor that will float in the water. If resistance is negligible, what is the shape of the path followed by the sensor? Oh, sorry, I don't think I relaunched the polling. Whoops. There we go. And we're almost there. We're almost there, guys. To quote Star Wars, almost there. Okay. So let's go ahead and see here. So just like if I release a projectile while I'm moving, this kind of behaves like a projectile. Originally, this object has, this is not a free body diagram. This probe, we're going to model it as a ball. It has a velocity sideways or northward, sorry, northward. So let me actually try to draw that so that this is northward. You know what? I'm going to say this way is north. This way is south. East is out of the page. West is into the page. Okay, so our submarine was traveling north, giving it some velocity in the northern direction. But because it's supposed to float, when we release it from water, it's going to accelerate upward. So the probe accelerates upward. And maintains a constant northward velocity or north velocity, northern velocity. So it's going to look like a ball that was launched horizontally, but accelerates upwards. And that's because eventually the velocity upwards is going to be greater than the sideways. And so our angle is going to increase more upward. So it'll be a parabolic path toward the north, curving upward. Ta-da! A straight horizontal path. If the acceleration was 0, then it would be a horizontal path like this. Or if for whatever reason there was some kind of force accelerating it sideways. So if A in the y equals 0, or A in the north direction is not 0, then we would get a straight horizontal path. Hopefully that makes sense there. But would it accelerate at a constant acceleration? Yes, because the buoyant force depends on the volume displaced. While it's under the water, that buoyant force is going to be the constant because it's still pushing out the volume equal to the volume of the probe. But as it starts to like rise out of the water, the buoyant force is going to be getting smaller and smaller and smaller until it equals the weight of the object. That's actually a really good question. That's actually kind of like, I think, something the AP might ask. So while it's fully submerged, as long as the gravitational field G is constant, the density of the fluid is constant, the volume displaced will be constant until it starts to come out of the water and less water is pushed out by the probe until it reaches the weight. Question 9. And I think I answered your question, but let me know if you have follow-up questions. A sphere of metal is placed in a liquid. The sphere sinks with an acceleration less than g due to a vertical buoyant force exerted by the liquid and the gravitational force on the sphere. Which of the following best represents these two forces? Ooh, sorry. Almost there. I really think we can finish like this entire set before you guys have to go. Alrighty. So it's sinking and it has an acceleration less than the acceleration due to gravity. So it's still accelerating downward, which means that the net force must be downward. Okay, I'm assuming you change your answer there. So because of that, we need to have more force down than we do up. You misclicked. It happens to the best of us. All righty. So hopefully we recognize that as long as this is not submerged in some kind of like sand or whatever, there's water underneath it pushing up, creating an upward buoyant force because the pressure on the bottom is greater than the pressure on the top. Dang, with the shade. Anyways, so they're not going to be equal. In this case, the acceleration would be 0. Here, the acceleration would be upward. Here, the acceleration is downward. And then here, this is if it were submerged. If it were submerged under sand and there was no water underneath it, then the buoyant force would be due to all the pressure of the water pushing down on it in this case. Okay, let's go ahead and look at number 10. We have a drag force, we have a buoyant force, and a weight, and they want us to determine a sphere is moving vertically in a liquid. The free body diagram shows the magnitude and directions of the forces exerted on the sphere at a particular instant. What is the magnitude of the acceleration and the direction of the sphere's motion? I kind of don't like that question here, but I'm going to assume it's been already doing this for some time. What the heck? My poll froze. And polling. Alrighty. Okay. So I think just to kind of rush things a little bit, yeah, the polling polling failed. So we have a net force of 9.2 newtons up. We have a weight of 8.6 newtons down. That gives us 0.6 newtons of force, oops, upward. Then we can get the acceleration by taking the net force, which is 0.6 newtons, dividing by the mass, which is going to be about 0.86. So this is 0.6 over 0.86. That's about 6 over 8-ish, which is going to be approximately 3/4. Let's see here. So it's going to be about 0.7, and it should hopefully be directed upwards since the net force is up. Check my math. Is for all I know, it's actually 0.6. Yeah, no, I think, okay. Couldn't it also be going down and slowing down? Yeah, I agree. That's why I don't like this scenario here because really this is the direction of the acceleration, not necessarily the motion. But we can determine it. That's a BDP right there. The drag force is up, which means that this thing has to be moving down. I see now. Okay. Because the resistance is up, this guy is moving down. So C is D. Yes. So originally, I guess I was relying on the fact that we should either know if it's slowing down or speeding up to get the direction of the motion. But no, the drag force tells us here which way it is. So very good. Kind of like helped me realize my mistake there, or pointed out my mistake. Oops. So the math is still correct. This is still 0.6 newtons over about 0.86 kilograms, which is approximately about 0.7-ish. So I still kind of agree with my magnitude there. If I feel like I made a mistake on the calculation, let me know. And yeah, dang, dude. Why am I teaching this class? Making all these silly mistakes. All righty. A block is submerged in a container of water that remains at rest with the only forces exerted on it being gravity and the forces exerted by the water. The force exerted by the water on the bottom of the block is greater than the force exerted by the water on the top of the block. Which of the following is an explanation of the microscopic cause of the difference in forces? All right. Hopefully here it looks like this bad boy is working again. This one's a weird question. Okay. No, not that one. All righty. So let's see here. Why do we think this might be a difference? So the block exerts a downward force equal to the block's weight. Well, that is a true statement, but I don't think it answers the difference in this. It has to do more with like something with the pressure or something like that. Okay. Yeah, this one was a guess. Okay. The net force exerted by the water on the block is equal in magnitude and opposite in direction to the force the block exerts on the water by Newton's third law. Kind of sounds okay. The molecules of the water hitting the bottom of the block have a greater average speed than those hitting the top of the block and thus exert a greater force. And then the contact force between the water and the bottom of the block is fundamentally due to interatomic forces. So I think A and B are out because they're not talking about microscopic quantities here. And then before I explain one or the other, I actually am a little weirded out by this question because I think D's are better answer choice, but I could also see C. Let me see here how they explain it. Bean chickles, it's not loading. Okay. Well, I think C is actually our better answer choice because if we remember, the force due to molecules is due to their change in momentum. So if I move faster on the bottom, I'm going to impart more momentum or momentum transfer than the particles on the bottom. And if we look at that like momentum transfer per time, that's the force. And so I actually think C is our best answer choice here. The contact force between the water and the bottom of the block is fundamentally due to interatomic electrical forces. But while this is true, I don't think it explains why the bottom exerts a greater force than the top. Yeah, this thing never loaded. I'll give you guys a better answer once this thing loads. In the meantime, we'll go ahead and move on to the next question. Oh, there we go. All right, so just real quick, just to make sure. And then just to kind of set us up for the next question, let's go ahead and look at number 12. And I'll give you guys the better answer once this bad boy loads. 4 cubes with equal volumes are at rest in a container of water as shown in the figure. The student claims that cube D is experiencing a greater number of water molecule collisions per second with its bottom surface than the other cubes. Which of the following indicates whether or not the student is correct and provides evidence for this? So while you guys are answering that one, let me go ahead and get bailed out by the College Board. Okay, yeah, C is correct. Okay. And it has to do with the differences in the surfaces. And it says that D, that while D is true and is a description of macroscopic causes, it does not address the difference in the interactions of at the two surfaces. Okay. Okay. Let's go ahead and look at this one here. We have our two answers. The student is correct because the bottom surface of cube D is deepest, which means the pressure is the greatest. Well, that sounds like what we've been saying before. I think that might be it. Let's just see here. The student is correct because cube D is the most massive cube and therefore exerts the largest gravitational force on the water molecules. We don't know that for sure. We know that it's the most dense, but not necessarily the most massive. C, the student is incorrect because cube C is the furthest out of water, so the pressure on the bottom of its surface is greatest. So remember that the pressure increases with depth. More than anything, what we can say is that this is the least dense of the 3 or of the 4. And because it's less into the water, the pressure here is going to be lower than all of these other guys, because remember that the pressure increases linearly with depth. So I don't think C. Student is incorrect because the cubes all have the same volume, so they experience the same number of collisions per second. Not true. Okay, so they're equal volumes. So then if they are equal volumes, actually this is the most massive, but that's not explaining this scenario of more collisions. So it will be B because pressure is due to these particles colliding on the surface. All right, we're almost there. Okay. So I'll record the video, but if you guys need to go here, it's fine. 2 metal cylinders of equal density and volume are submerged in water and remain at rest with their top surfaces at the same height. Cylinder A has a smaller height and larger cross-sectional area than B. Which of the following explains why the force exerted on the top of the cylinder A is greater than the force? All right, have a good day, y'all. Take it easy. Why the force exerted on the top of the cylinder is greater than the force exerted on the top of cylinder B. So let's see here what we are thinking. Oh man, not now. We need a restart. Let's relaunch the polling. Okay, so the top surfaces are at the same height. Okay. Okay. So I guess the way I see it is the pressure is going to be the same. Keep clicking on the buttons on my pen. So the pressure is going to be the same on the top surface of both cylinders because they're at the same height. So the pressure on A is equal to the pressure on B. So I think we're going to have the same average speed for the collisions because this collision is going to impart a tiny little force on a tiny little area. So let's see here. The water molecules striking the top surface of cylinder A have the same average speed as the water molecules striking the top of surface of cylinder B, I think. But more than anything, the force here is going to be over a larger area. So while the pressure is the same, the area is going to be greater on A than the area on B. And if we look, force equals pressure times area. And so I think B is our best answer choice. Let's see here. The difference in the average speed of the water molecules striking the top and the bottom surface of A is less than that of B. This is a true statement, right? Because as we go deeper, the pressure increases. So I definitely agree that the pressure here at the bottom of B is going to be greater than the pressure at the bottom of A. And while this is a true statement, I don't think that this explains why the force on top A is greater. If anything, if it stays in equilibrium, then the force here would kind of, I think I was gonna like talk myself into like a logic trap. Let me see why they say C is not the best answer choice, just to make sure. So they say C. Since the difference in depth is less for cylinder A, the difference in pressure and thus the difference in speeds is less. And they're saying it is, what the heck? They're just restating their answer choice. Here, let me show you. New share, and then, okay. So the difference in the average speed of the water molecule striking the top surface and the bottom surface of cylinder A is less than that of cylinder B. And then what do they say? The difference in depth is less than for cylinder A. So the difference in pressure and thus the difference in speeds is less. Oh, maybe here the sentence reads that the top and the bottom, the difference between the top and the bottom. No, that's still, yeah, I don't know. I think they're kind of like, that's not a good explanation. But let me know if that kind of answered your question there. Yeah, it just restates the answer. That's kind of how I feel it is. So I don't know, kind of a bad explanation. But it is true, but I don't think it explains why the force exerted on top A is greater. Which is what, wait, did I choose the wrong answer choice? Oh, no, yeah, they say B is correct. Okay, all right. Okay. The small dots in the figure represent the molecules of a solid object and the dashed lines represent the molecular bonds between them. The large dots represent the molecules of a liquid in which the object floats. Which of the following? Oh, you got to go now? All right, no problem. We'll see you again. Have a good week until then. Which of the following best describes the force that explains the interaction of the object and the liquid? So the electrical force that repels the electrons of the object's molecules and the electrons of the liquid molecules, I think that is going to be it. The molecular bonds between the molecules of the bond and the molecules of the liquid. There are no molecular bonds between the object and the molecules of the liquid, so not true. The strong nuclear force, not the case. The strong nuclear force has to deal within like the nucleus here. And here we're talking about intramolecular forces or bonds, which happens to be the electron cloud and the electrical forces. And then the gravitational attraction between all the molecules is present. So while these guys are all definitely gravitationally attracted to each other, that is not going to explain the interaction where this guy pushes or these molecules push the fluid's molecules out of the way. It has to do more with the electric force, which is much greater than the gravitational force. And so that's it for today's session. I'll go ahead and pause the recording here or stop the recording here. But those are the questions for